This lab explores the activity that involves the area functions and fundamental theorem of calculus. Students at the beginning are asked to consider what happens when you have a area compiling function, where you look at compiling the area from a starting point to various endpoints when we look at the integral. So it's the first main question asks them to consider the situation, and we have a graph that enables them to do that. So they're asked to go back to the previous page, and in particular to pay attention to the numerical value of area that is displayed on the screen, and to describe when it's increasing, when it's decreasing, those sorts of behaviors that we're used to talking about with differential calculus. So they can come back here and they're asked to pull on X and watch what happens as the area is compiled, and to kind of denote and mark down what their observations are. Okay, then after they have messed around with that for a while, they're asked to predict the movement that they would see if they actually plotted the area function. So on this graph they actually have a point P that represents this numerical value of area, and so they're asked to see if the path of this particle describes what they expected to happen on the previous one where it wasn't present. So they can drag it, and then they can actually watch the behavior of P as it goes. So now we're connecting numerical and graphical representations. Now they're actually asked to say, all right, well, what if you want to actually see the locus of this point? And so they're asked to actually go back and plot the locus, so they can actually go to their menu command, go down and construct a locus. The locus of P as X moves, and there they get it. Again, asked to describe whether or not that matches what their expectations were. Then they're now moved into a second part of the lab where they're going to look at the connection with slopes and slope fields. So here they're asked to consider a situation where a function defines the slope of a previous function. And what would that look like? So they're allowed to define a function, we're calling it slope of x, to be anything they want. In this case we're going to start with sine of x. And then they're going to plot a slope field. So now this generates, each of these line segments represents the slope of some other function. Okay, after looking at it, they're asked to compare how the graph that they produced with the locus command earlier compares to the slope field. Okay, then after that they're asked to explore this in a graphical sense, where they're going to drag around A, which is the lower limit of integration, to see the effects on changing the lower limit of integration, and they're asked to describe the behavior they see. So in this case they're going to grab a hold of A, this here, and they're going to watch the behavior of the locus, and so hopefully they'll notice that they get a vertical shift one way or the other. Okay, after they explore that, then they're asked to go and explore this on top of a slope field, where they can actually drag the upper limit of integration. And so here they grab a hold of the upper limit of integration and pull it. And we have a split screen where you can actually see the area function along with the area point, this one right here, coming out and being visible. And then as we wrap up the lab, we say, all right, suppose you look at manipulating not x, but a, the lower limit of integration. What sort of effects would that have? So they're asked to go back, and they're going to look at manipulating a here, and they can see that it moves up and down on the slope field, but yet always maintains a shape similar to the slope field, no matter where it is. And then finally they're asked to summarize what they notice about the relationship between area functions and derivatives.